Hey everyone. So 5:40. So let's get started with today's lecture. So this week, for week 10, we'll be focusing on big tech's recommendation systems and ethics. So basically, we'll just be kind of like looking at everything that we've learned about like theoretically in the past few weeks and kind of seeing how it's applied in industry today. So there's just some administrivia. So we'll have a quiz that'll be released soon. That's going to be due this Friday, and that'll be the last quiz. We'll have the last homework that's due Wednesday. By before the start, before like on the day of the when the next lecture is supposed to be. Um, and then November 30th at 11:59, we'll actually have a final project due, and we'll talk about details of this at the end of the lecture. So today is actually the second to last lecture, sadly. No lecture next week though because of Thanksgiving. So you might have noticed on the syllabus that there's supposed to be a lecture next week. So what we'll do is just kind of last the lecture content that we'll be missing. We'll kind of just add it on to the last lecture on December 1st. And so we'll be talking about briefly decision-making psychology and security. We'll have project presentations, which I'll talk about at the end of lecture, and then just a finale recap of the course and next steps. So this is an overview of what we'll be talking about today. So first, let's get started with talking about big tech's recommendation systems. So this lecture is going to be a different format compared to other lectures. So in other lectures, we learned about kind of theoretical way of thinking about recommendation systems. So the different ways that recommendation systems exist and the math and all of that. But now we'll be kind of going case by case through different companies like Facebook, Google, etc. See how they're deploying recommendation systems, what concepts they're using, and also like problems that they face and how they're like solve these problems. So this will be kind of a very highly applied lecture. So as we've seen throughout the course, recommendation systems are used by almost like every big tech company and almost like every company these days. So we explore two paradigms, right? That they're content-based recommendation systems and collaborative recommendation systems. So content-based systems look at the actual content in the ecosystem. So for Google News, it would look directly at news articles, like what genre is the news article, what words does it use, is it fake news, etc. And similarly, Facebook will look at the content of the post. So it's a primarily content-based system. But then we also have primarily collaborative systems like Amazon. And you might be familiar with the section that says people who bought the item also bought. And it uses a collaborative filtering approach to determine how people buy items. And similarly for Netflix, it will look at the viewing history of different users and compare similar users to determine recommendations in the future. But just as a side note, note that most of these companies likely use hybrid systems that incorporate both content-based and collaborative algorithms. So even though I say primarily content-based, primarily collaborative, all of these recommendation systems likely use both content-based and collaborative systems within them. So now we'll be talking about Google as like our first company to look at. So Google is a huge business, right? Their parent company Alphabet owns like dozens of companies, and each one of them have dozens of recommendation systems that they use. So Google itself, very interestingly enough, is shifting from a search engine to a recommendation system a little bit. So if you look back at the 90s when Google was actually made, it used this algorithm called PageRank, which is purely just a mathematical algorithm that looked at whether how users viewed pages and how relevant it was to the search query. But now Google is slightly personalizing its recommendations on its search engine so that it uses the user attributes. So for example, your location, your previous clicks and behavior, etc. So if you're from like France, it's much more likely to show you French art web pages than it is English web pages. And it'll also use previous clicks and behavior to kind of show you similar content to what you've been seeing. YouTube is definitely uses a recommendation system. So it uses your watch history to show predict what you'll see in the future. And it also has something called serendipity. So serendipity, which we talked about a little bit in the first lecture, is where you show slightly unrelated results your to what's being recommended. So let's say that that you like cats a lot, then YouTube will recommend you a bunch of cat videos. But you also don't want to see hundreds of cat videos like for hours and hours. Like you will get bored of that. So what will happen is YouTube will show slightly unrelated content. So maybe dog videos or other animal related videos. So it'll slightly stray off so that you have this like feeling of serendipity or like seeing like new stuff. And then Google News recommends news articles, and then Gmail recommends words when you type in email. And we'll talk about Gmail's a bit more in depth later. So as a brief aside, there's a problem in reinforcement learning called exploration versus exploitation, which some of you may have heard of. If not, that's okay. Basically, what exploration versus exploitation talks about is in machine learning, specifically in reinforcement learning, you have this problem where initially you don't know much about the environment that you're in, right? So let's say that you're like a bot that plays chess. Initially you don't know much about the game except for a few rules, so you kind of just make random moves to begin with and try to see how they work. So you might move a pawn, and then you might move a queen, and then you might move see that, okay, maybe I should not act this way, or maybe I should act this way. But over time, once you've learned more and more about the game, if you still keep making random moves, that's kind of suboptimal, right? Because by that point you've realized what is a good move. So then you slowly shift to the exploitation stage where you exploit the moves that you know are already going to benefit you. And you can kind of bring that idea into recommendation systems, and you'll see that a lot, is that when a recommendation system starts out, right, you have this cold start problem where you don't know much about what the users like, much about the items themselves. So what you do is you start out in the exploration phase. So let's say you're Google News and you're recommending new news articles. If you don't know much about the user, then you have to display something on the screen, right? So what you do is you just show random news articles, and ideally in like unrelated genres and topics, to figure out whether you like them. So then after showing you 20 news articles, it will realize, okay, these two are the ones that you really like a lot. And then after doing this for a bit, maybe a few weeks, then it realizes, okay, you really like reading business articles and sports articles. So then it slightly shifts to the exploitation stage where it recommends from those genres that it knows that you like. So instead of recommending you fully random articles, maybe a few weeks down the line, it'll recommend you more business and sports articles. So a key question designing recommendation systems is, how do you balance figuring out more of what you like versus showing articles that it already knows that you like? And you can kind of see this in action here. So the basically here, let's say you have like 8 different actions, right? So this is like generally this is more reinforcement learning related, but if you kind of see it in recommendation systems, each action can represent like an article that you choose to display. So article 1 may be business article 2 might be a sports article. So what happens is that if you just do just pure exploitation, when you start out the system, you see that you always choose action 5, right? And action 5 may or may not necessarily be the best article for you to show, right? Whereas you have something called an epsilon greedy policy, which we'll talk about in the next slide, where you kind of do exploration and exploitation. So with a certain probability, you explore, and with a certain probability, you exploit. So you can see like we kind of take some random actions. Sometimes like we choose article 0, 1, 2, 3, etc. But then most of the time we actually choose stick with choosing article 5, because the system probably realized that article 5 is something that you really like. And then a decaying epsilon greedy policy is similar, except that we slowly shift from exploration to exploitation more and more. So you can see how in the orange graph, it's kind of like an even distribution. Like you kind of always do a little bit of exploration, but in the green graph, you can see that towards the right of the graph, there's less and less like scattered points, because the system has realized that you really like article 7, and then you're very confident on choosing the article. So as the graph was saying, and as I was mentioning too, there's something called an epsilon greedy policy and a decaying epsilon greedy policy. And it's very simple. So you train your recommendation system, and then so that it predicts like a recommendation for each user. And then on screen, with a certain probability, we'll call that probability epsilon, we show that recommendation that the recommendation system outputted, right? So that's exploitation. But we also want to figure out whether the user really likes different types of articles. So then with probability 1 minus epsilon, we provide a random recommendation. So we'll just show them a random news article. And you can kind of see here in the previous graph where we kind of do a little bit of both, right? Like all of these gathered points are exploration. And then here, this is exploitation of choosing that one, our article 7. And a decaying epsilon greedy policy is the same, except all we do is we just exponentially decay epsilon. So what happens in that case is that we shift slowly from exploration to exploitation. So in epsilon greedy, we kind of just maintain the same balance between the two, but in decaying, we eventually converge to full exploitation. And if you're interested in this, you should take CS 188 and CS 285 because they talk about these in more detail. And here you can kind of see the results of these running these different policies. So cumulative average reward is, you can just think of that as like how much the recommendation system outputs like a good recommendation. So you can see with the blue line, that's just only doing exploitation. So the reward is like 0.75, right? And then epsilon greedy, you can see that it's actually way higher because it was able to find new recommendations that it thinks that you like. And you can see that the decaying epsilon greedy policy works even better because it slowly shifts from exploration to exploitation, right? Because after a certain amount of time, you kind of already know what the user wants. So then you can just fully converge to exploitation. And now we'll be moving on to talking about Gmail. So a problem that Gmail faces is that it builds millions of like miniature models, right? So where this happens is in something called Smart Compose. So Smart Compose is a text generation recommender that helps you autocomplete your emails. And you've likely used this before where you type an email and it predicts the next few words that you're typing. And most of the time, or at least sometimes, the recommendations are pretty accurate. And how Gmail does this behind the hood is it combines a large model using LSTMs and state-of-the-art methods. Those are like just NLP, like fancy NLP models. So it uses one large model for the entire platform, but then it also has one personalized model per person, so that each personalized model learns how you specifically type. That's different from how everybody else types. So the problem we have here is we have to give each person their own recommendation model. So there's definitely going to be a trade-off between accuracy and efficiency. So that large model that Gmail used, we could actually just make millions of those, right, for each person, and we'd have extremely accurate recommendations. But if it takes 4 or 5 seconds for Gmail to give you a recommendation every time you type, you're likely not going to use that feature at all, right? So there's this trade-off between how big and accurate your model is versus how efficient you want it to be. So each person's recommendation model also has to be fine-tuned, right? Because it's not just like a one-time thing that you run and that's it. You have to keep training the model like maybe every month, every few months, because your writing style will inevitably change. And can we feasibly train like 100 million parameter model over 1.5 billion Gmail users? Which is like 150 trillion parameters every few months. That's definitely not possible. So that's why Gmail has to kind of address that trade-off. So what it does is instead of running a neural network, it actually uses something called the ngram algorithm, which again, this is kind of talked about in CS 188 a little bit, but basically it's just a simple just set of formulas where you just kind of predict what are the most likely words that are going to come after the words that you've already typed. And it's just a simple math formula, as you can see here, just like summations and products of probabilities. So because of that, it runs in the order of microseconds at maximum like milliseconds. And this is based on the hypothesis that Gmail's large central model will capture the structure of language, right? So it'll understand how verbs and nouns appear in a sentence so that if you type a certain word, it can predict the next word accurately. But you don't need that large of a model to like kind of capture your style, right? Like you're not writing completely different to other people. Like you still like follow grammatical English normally. So that's why you can use like a miniature model like ngram to like capture your specific style. And yeah, so that was just a little bit about Google's recommendation systems. Let me just check the chat if there are any questions. Can you please get a link to the slides? Yeah, after the end of lecture, I will post these slides and on Piazza as well. So now we will be talking about YouTube's recommendation systems. So YouTube's recommendation system at a glance, so they actually describe it in a paper. So Google Brain basically had a paper called Deep Neural Networks for YouTube Recommendations, and they actually talk about how YouTube's recommendation system is built. So how it works is like from a glance, it's kind of simple. So you have a video corpus, right, which is basically just like all of YouTube's videos, and then from that you have to like shortlist potential recommendations, right? Because if we run a recommendation system that chooses from billions of videos, it will take forever to run, right? So you need an efficient way to like generate potential video candidates. So that's the candidate generation phase. And then from that, we rank like the hundreds of videos that are outputted, right? So from candidate generation, we get 100 videos. And then from those hundreds of videos, we rank them like, what are you like most likely to watch out of those 100 so that it maximizes the amount of time you spend on the platform. And both of those are informed by your user history and context, as well as like the actual features of the video. And we'll be talking about candidate generation and ranking in more detail now. So candidate generation, and especially in the paper, they tackle a few problems. So they pose recommendation as a classification problem. And recall from lecture 2 that classification in machine learning is when you try to predict whether an image or a sentence or like a file is of certain categories. So for example, if your news article, a classification algorithm would classify it as like a sports article, a business article, a weather article, something like that. So YouTube, interestingly enough, poses recommendation as a classification problem. So they try to find the probability that what you will watch right now, which is W sub T, given some user information U and the context C. So this is just like a very fancy mathematical way of saying we're trying to classify which video you're going to watch in like right now. And basically, again, this is just a fancy operation called softmax, which is used a bunch in machine learning. Basically, you can just think of this as like a huge vector of probabilities where each entry corresponds to one video, and we choose the highest video. We choose the video based on the highest probability of what you will watch. Um, that the algorithm will like has to select from millions of videos, right? So we can't go over every video in YouTube and query every single video and then choose, okay, let's select this video, right? Because that's infeasible by the amount of videos. So there's this technique called candidate sampling where and it's used a bunch in machine learning, where if you have a classification problem with way too many classes like we do here, then instead of like going over every single class, we basically calculate the probabilities for only a subset of all the videos. So we just randomly sample from all the videos, calculate the probabilities that you will watch that video, and then we kind of just extrapolate that to other videos by predicting how like that probability is calculated. And you can see that candidate sampling is actually like a very like explored field in machine learning. So there's actually many techniques like noise contrastive estimation, negative sampling, etc. But we won't be going into those. And in the paper, they actually they actually show like the submodule of candidate generation here. So it looks very complicated, but honestly, it's pretty simple. All it does is you have the lowest layer here, right? Which has a watch vector, search vector, geographic embedding, age, gender, etc. Basically, all of this is just the user info and the context, right? Like what's your age, what's your gender, what's your like, where are you? Like, are you in the US? Are you in France? And then it takes your watch history, right? So it takes your watch history and creates an embedding. And an embedding we'll talk about later. It's just a numerical way to represent like some like a value. And it does the same thing for your search query. So if you keep searching cat videos, then it will realize that, okay, you probably want a cat video to be recommended to you. And then these ReLU layers are ReLU, all it is just like an operation that's used within your neural network. So you can kind of imagine that all these red layers are just like different layers in a neural network. So you pass in these inputs, pass it through your neural network, and then you get this user vector U, and you get video vectors VJ. Basically, all that means is it just gives you the probabilities that you'll watch a certain video based on what user you are. And if we actually go back, so we just talked about candidate generation, there's also ranking. So now we'll talk about ranking. So one aspect of ranking is that, let's say we have 100 videos now and we want to prioritize which ones we show to the user. So there's a whole sub branch of machine learning called feature engineering that is very well studied, where basically you're given data, right, for any machine learning problem. Let's say you're predicting house prices. Some data is like numerical, which is pretty easy. Like let's say the number of bathrooms, the number of bedrooms, but there's also some data that's not numerical, right? Like for example, what country it's in. Like countries, you can't represent a country as a number, right? Like you can only represent it as like the US, the US, like Canada, etc. So yeah, basically these are just different types of features that are incorporated into the algorithm. So binary features are like Boolean, yes or no, whether the user is logged in. Then there are features with millions of possible values, like the user's last search query. So we need an efficient way to kind of like encode millions of possible values within like a few set of values. There's univalent features, which is like for example, the last video that you watched. But then there's also multivalent features, which is the collection of the last n videos that you watched. And you use different in different scenarios. And then there's also like the properties of the actual video versus the properties of the user, which are called impressions and queries. So there's just like a lot of terminology here because it's like a very well studied field. But just know that feature engineering is we want to take different things we know about the data and translate that into something that the machine learning model can operate on. And as we talked about in the deep learning lecture, deep learning like revolutionized ML because most of the times what you do is just shove all the data that you have. You don't have to worry that much about it, and then just like let the machine learning model like figure out all the patterns and like whether patterns exist or not, right? So the magic of deep learning is that shove all the features that you know. So like the whatever you know about the user, about the video, like everything that you have on your platform, let the network train. It'll probably be pretty slow because you're shoving all the data you possibly can, so your model's going to be pretty big. Then see the top features that are highly used, right? So maybe some data that Google has about you is like, let's say like your birthday. Maybe your birthday doesn't correlate that much to what videos that you watch, right? And if it doesn't, then you'll kind of see in the actual weights of the neural network that they'll almost be zeroed out. And then from that, we can kind of detect that, okay, we don't need age because it's just like occupying space and time in predicting, making predictions. So let's make a new model that doesn't need all that highly like uncorrelated data. And here is basically ranking in action. So very similar to before, what we do is just all the information that we have about the video and the user. So here, like for example, the impression video ID, the user language, the video language, the time since the last watch, the previous impressions. We put all this data, shove it into a neural network, let it do its thing, and then it will basically give you a bunch of probabilities of how likely you're going to watch the video. And then since we're showing maybe like 10 or 20 videos that you want to watch, you will rank them based on the probability that you watch this video, the second most likely video that you'll watch, etc. And you can kind of see here like the square root of x squared. This is a concept in feature engineering where if you have some sort of numerical value, then in order to help your neural network train faster, you kind of do some basic arithmetic operations like squaring, taking the square root, maybe taking the log, and then just passing that into the neural network. So that just makes it like potentially have more accuracy. So yeah, just a recommendation, as a recap for the YouTube recommendation system, basically it has two blocks, the candidate generation block and the ranking block. Candidate generation shortlists millions of possible videos into hundreds, and then ranking takes those hundreds of videos and ranks them based on how likely you are to watch them. So behind all of like behind all of this is just like basic neural network math. Even though it looks complicated, it's actually pretty simple in practice. And now we'll be talking about Facebook or Meta and how they use recommendation systems. So how Facebook came into the game was by really revolutionizing ad tech. So advertisements in the old days prior to recommendation systems had this basically they would have these curated commercial breaks, right? And I'm sure you all experienced this, where you'll see a bunch of ads that are really not related to you at all. Like marketers will try to guess what kinds of users watch a TV channel. So obviously, like if you're watching the Disney Channel or Nickelodeon, it's gonna recommend like kids' toys advertisements rather than like a credit card advertisement, right? But even despite that, like out of kids, there are like hundreds of millions of them, and they have very different like preferences. So basically, advertisements weren't that well catered to the audiences, and the conversion rates were like much lower than they are now. So ad tech now is crazy because now we can use machine learning models to do that process of like trying to guess what kinds of users watch a TV channel, right? Just literally shove in all the history and all the like the user data that you have, and the machine learning model will kind of find all the correlations that, okay, maybe at 5:30 p.m. For Nickelodeon, people come back from school, so they watch like this kind of, they're more likely to watch this kind of advertisement. So ads that are related by content or user interaction are recommended. And the result of this is that everyone benefits, right? Consumers benefit because they get products catered to them that are more likely that they will enjoy more, right? And then advertisers obviously benefit because more consumers are buying their products. And the ad platform usually takes some kind of cut out of the advertisers, so they also benefit. So it kind of benefits everyone. So before we go in, like in depth into Facebook's recommendation system, we'll talk about feature representation. So this is very closely related to feature engineering that we were talking about earlier, right? So let's say we have a lot of different features in our models, right? And the one that we'll talk about here is categorical features. So as I was mentioning earlier, like country is a categorical feature, right? Because your options for countries aren't like 0, 1, 2, 3. They're like the USA, Canada, Mexico, etc. So here, similarly for genre, we have the options of hip hop, pop, rock, R&B, and maybe there are others, but we'll just keep these four for now, just to keep it simple. And how do we transform these into meaningful representations that our models can learn from, right? So the one really common way to do that is called one-hot encoding. So instead of one feature representing the genre, we make n features, right? So like maybe a categorical variable would be genre, and that possible values could be hip hop, pop, rock, and R&B. But here we actually have four different variables, which are all binary or Boolean. So we have a is hip hop variable, is pop variable, is rock variable, and is R&B variable. So if a song is pop, then basically we pass in this vector into the model. Oh, it looks like there's a typo, but basically it should be 0, 1, 0, 0, because it is pop, but it's not anything else, right? So we pass four different variables now into the model, and now it can like more meaningfully learn from how like different values in the categories correspond to the outputs. And then now we'll be talking about something that's like pretty important in not even just recommendation systems, but just machine learning in general. And that's the concept of embeddings. So we do one-hot encoding, and maybe for other types of data, there are other like data processing methods, but these are all manual and like they're not fully comprehensive. If you just directly pass this into a model, you won't get that great of an accuracy. And the reason why is because we're kind of like not meaningfully representing them, right? So this is kind of like an abstract topic, but like if you have is hip hop, is pop, is rock, and is R&B, we're kind of creating like a four-dimensional vector, and we kind of in this four-dimensional space have different songs, right? But maybe hip hop is like more closely related to pop, or sorry, no, hip hop is like more closely related to R&B, right? So by like distance, the vector for hip hop is like equidistant from the vector from R&B as it is from pop and rock, right? But hip hop is a little bit like more related to R&B than it is to pop and rock, right? So ideally, you want to create some kind of vector that is like close to R&B for hip hop, but it's like far from pop and rock, right? And basically, that's what embeddings do. Embeddings basically project vectors from a lower dimensional space into a higher dimensional space. So you might have learned about vector projection in like Math 54 or EC16A. And here it's just kind of done, but like on steroids. So instead of like maybe a 10-dimensional vector, we might project that into like hundreds of dimensions, or sometimes we also like downsample them. So basically we learn a neural network that takes an m-dimensional input and then outputs an n-dimensional input, where m is less than n. So you can kind of see here, like we in the left graph, we have some kind of three-dimensional space. So let's say we have three features that we pass into our model, and it creates this kind of curvy shape, right? But then if we were to project that down into 2D space, then we can actually see how the data is in like a 2D space, right? So by doing these embeddings, we can learn much more meaningful representations so that our models train better and have high accuracy. So, and again, so it might be a little bit hard to like initially grasp for concepts about grasp like how embeddings work. So I'll just like give a few examples here of how like if we had an embedding, why it would be useful. So as I was talking about earlier, right, like certain genres are more related than others. We have the same concept in words, right? Like in the English language, if you're trying to build some kind of like language model, then we know that the words cold and freezing are like very close in like meaning, right? So then in this embedding space, we would want the distance between the cold vector and the freezing vector to also be pretty small. And whereas the vector for cold and the vector for the word apple would be kind of far apart because they're not really that close to each other, right? So if you're to like have a language model that sees the word it is a cold day, then it'll also be similar in meaning to it is a freezing day, just numerically, right? So that's the power of embeddings. And then the way that's used in recommendation systems is to model the items themselves. So if we have posts, right, we'll have billions, maybe trillions of posts that are on Facebook. We'd like posts that are similar in content to be closer in Euclidean distance in the embedding space. So if we have a bunch of articles about, or a bunch of posts about the election, then they'll be close in this embedding space just by distance, right? Because each article will basically be a vector and we calculate the distance between the vectors and they'll be pretty small. So how embeddings are used in neural networks is you can kind of see it here. Especially in this blue part, we this is basically a digit classification model. So we take handwritten digits and we try to predict whether the number that was drawn was 0 through 9. So we have the raw bitmap of the hand-drawn digit, which is basically just like all the pixels. And you can kind of see that there's like there's a huge number of connections between the hand-drawn digit and a three-dimensional embedding. So basically this three-dimensional embedding is a way to represent millions of pixels in just 3 values, right? And that's very powerful because we can compress like a very large representation to small representation so that our neural network can learn from more meaningful data. But there's also a problem to this, right? Which you'll see all across machine learning. When you have a more meaningful representation, when you have a more accurate model, very likely that's because you make your neural network bigger. So because you make your neural network bigger here, you can see all these different connections add to the time that it takes to calculate the final value, and it adds to the compute power. So you'll actually see in practice that embeddings make up almost a majority of the size that a neural network takes up. And because of this, we need to find ways to efficiently calculate these embeddings, because that's the main bottleneck in doing predictions on neural networks. And the way Facebook tackles this, which is bringing it back to how it's applied in industry, is the butterfly shuffle method. And the actual details of the algorithm aren't too important. It's just the idea of dealing with parallelism, right? So basically you have a bunch of different data and you have different devices here, which are specialized for certain types of data. And then it kind of just mixes and shuffles them for to make the data combine together at the end. And this is actually described in one of Facebook's papers called Deep Learning Recommendation Model for Personalization and Recommendation Systems, published in 2019. And basically how it works, again, you don't really have to understand this too in depth, but imagine that you have a bunch of data and basically each color represents a different data point. So we have data points we have the data points blue, green, and yellow, but we each of these data points have to be predicted from a bunch of features, right? So we have to let's say the output is uh, for the news articles, and then for the input, it's a bunch of features of the news article. So you can see that each news article will have one blue feature, one green feature, and one yellow feature. And then we kind of have mix and match through the butterfly shuffle. So in the input, basically there's model parallelism, which is basically each device is specialized to look up a specific embedding feature. So let's say the feature is whether a post is fake news. Device one specializes on determining whether a post is fake news. So you might maybe even adjust the hardware so that it runs those computations more effectively. Whereas device two might detect whether a post is spam or something like that. And then you pass in the data for each of these model parallel for each of these feature specific devices. Then you do this butterfly shuffle, as you can see here. And then at the end, you have data parallelism, right? Because device one has all of the features for data point one, device two has all the features for data point two, and device three has all the features for data point three. So now you can actually run this model using like multi-threading or concurrency to make your model run faster, right? But the way it makes this run faster is by having devices specialize in different types of embedding features. So as a result, like the main bottleneck, which is embedding, becomes way faster. And that's why Facebook's butterfly shuffle method is kind of it was like revolutionary. And then they talk about also so Facebook abbreviates its like deep learning recommendation model as DLRM, and here it just kind of gives you an overview of how the model works. So it just has different aspects like the inputs from the network, which is like a bunch of features. EMP, EMB, these are basically just like looking up embeddings. Feature interaction is just kind of like concatenating all those results together, like through the butterfly shuffle method. And then lastly, the top MLP. MLP is like multi-layer perceptron, right, or neural network. So you pass in all of this work into the neural network at the end. And you can see like each part is has some kind of certain domination to it. And basically what this means is like so memory capacity constraint means that a lot of Facebook's memory storage is being used in storing all the embedding tables, right? Because as we were talking about earlier, like embeddings take up a lot of space in neural networks. Memory bandwidth constraint means that in looking up these embeddings in these table, the hardware is not as parallelizable. Communication constraint is we have to concatenate a bunch of results together, right? So in the butterfly shuffle method, we need all the devices to talk to each other so that it like moves the data to the right place. So there's a bottleneck here created from like the actual communication. And lastly, we're compute constrained in the last layer of the uh, of the model for the actual neural network, right? Because as we know, neural networks, like they take up a lot of compute power. So each of the layers, especially when you make the model bigger, waste a lot of processor resources. So as Facebook was designing its system for each of these four like parts, it had to keep each of these constraints in mind and make the algorithms more efficient in each of these regards. Okay, and now we will talk about Facebook. And let me just address a question by Jenny. So Jenny asked, is the Ngram model personalized for each user? Yes. So that's where like Google's recommendation system, what they do is they have one large main model, but that uses like a transformer LSTM, which is basically like a fancy NLP model. But then it has a personalized Ngram model per user because an Ngram model is very like it's very efficient and it's small. Okay, and yeah, now we will move on to Amazon. Because we've already covered like the thing is many of these companies like deal with the same problems. Like YouTube's video recommendation is very similar to Netflix's movie recommendation, so I won't be like going over each of those things over and over again. I'll just like, for example, for Amazon and Netflix, go over stuff that maybe that Google, YouTube, and Facebook didn't think about or what they specifically invented. So just as an overview of Amazon, which I'm pretty sure all of you know about, is it's an e-commerce website, right? And online shopping websites formerly had people curate lists of items to buy, places to see, etc. So you would have these like experts who are like foodies or like who traveled a lot, and they would kind of tell you that, okay, you should eat at this restaurant, you should buy this item, you should go see this place. But these are very highly subjective lists, and these are also very general lists, right? Like the top, if there's an article online, the top 10 places to see in Paris, that's what, if you take everyone's opinion together, that's what you would see. But maybe you're specifically interested in food, right? So maybe you only care about the bakeries and the restaurants. So then you don't care about that list as much, right? So just like with ad tech, for advertisements formerly, they didn't have that like level of person. But recommendation systems brought mass customization by basically allowing you to like automatically generate these lists of items and having it curated by an algorithm, right? So now when you go shop on Amazon, it recommends that, okay, you should buy this item, that you should buy this item based on what other people bought. So people are now buying things that they might not urgently need, right? Which you could view that as negative or positive, but but a lot of people view it in a positive light where like now customers are being connected with products that they more like to like engage with, right? And this is a result for why Amazon's growth has been like almost exponential over the past few years. So Prime Video, which is basically the Netflix analog for Amazon, right? They had their own unique problem where they had a bunch of data about what like movies a user watched, but the problem is the thing is like this data is sequential, right? And normally neural networks don't care about the ordering of the data. You just kind of shove in the data and it just like kind of figures out the connections. But stuff that you watched 1 week ago, that you watched a few months ago, are much more likely for you to use than like some stuff that you watched 10 or 20 years ago, right? So you don't want to have that be more correlated to your recommendation next week, right? So in Amazon has an article where they talk about their recommendation algorithm, and you can see the name of that article here. And just again, as a brief aside to kind of explain to have you understand the algorithm a little bit better. So as we learned about a few weeks ago, there's a specific type of model called an autoencoder. And an autoencoder is very simple. So you have a deep learning network, right? You have data passed through different layers. So sometimes you will have the neural network like compress the data down. Sometimes you might have it like upscale it, right? So an autoencoder kind of combines both of those ideas together. So let's say you have like an image, right? You have an image of a cat, you have an image of a dog, etc. But you don't want to store like megabytes of data for each image, right? You don't really care about the image being exact, right? So this is not for the purpose of like displaying images to the user, right? Because you want the images that you see to be very crisp in quality. But let's say you're looking at recommendations, right? A cat that's like slightly to the left versus slightly to the right doesn't really matter in the eyes of the recommendation system. So you can kind of lose a little bit of the detail. So you take the image like vector, right? So you can take the image, which is like, let's say it's a 1920 by 1080 pixel image, and it has like the red, green, and blue values. You could just like flatten that into one vector, pass that into a neural network through progressively smaller and smaller layers, and you create something called an information bottleneck. Which basically means that you're forcing the model to represent this image in a smaller number of values. So in the maybe like millions of values that are there in a 1920 by 1080 by 3 vector, maybe you only wanted to store like the content of the image in maybe like 50 or maybe 100 like values. So that's the latent space representation, where we have this compressed representation of the original image. And then what we want to do is, once we have this compressed representation, we want to like recover the image from that, right? So what we do is a decoder, and the decoder is basically just like the opposite of the encoder. So if we had layers that progressively started from larger and went down to smaller, then for a decoder, it would start from smaller and then go progressively larger. So that's how an encoder and decoder work. You usually use them in parallel in training, and then you can kind of take those parts apart, and then you can use them separately later on. So through an autoencoder, you can take something that's very high dimensional and represent it in a very low dimensional space. And as we were talking about in embeddings, right? There's more than so one obvious advantage is like the less memory use, right? Because instead of having millions of values to represent one image, now you only need maybe 50 or 100. But there's also a second, actually more important advantage, is that the encoded representation is more meaningful, right? Because the model is forced to learn a lower dimensional representation. If that happens, then it has to be smart about how to compress the representation, right? And we know that neural networks are basically just like they approximate functions, right? Like at the very core of it, a neural network just basically tries to approximate like maybe 1,000-degree or million-degree polynomial. And we know from how polynomials work that slight changes in the input will only lead to slight changes in the output, right? And if the neural network is learning a very meaningful representation in a lower dimensional space, that means that slight changes in that encoded latent space representation will only lead to slight changes in the output decoded representation. So that's really the main advantage of autoencoding, is that we create more meaning out of the data. And yeah, I think I forgot to add the slide here, but basically how I'll just go back here. So how Prime Video used autoencoders is that they initially had this naive model where it didn't work that well. Like they compared it to like some of the state-of-the-art recommendation algorithms, and they couldn't really get Prime Video to output that great of a quality of recommendations. So what they did is they used autoencoders to take all of these movies, project them onto this lower dimensional space. And once you do that, you have a more meaningful representation. So then Prime Video's recommendation algorithm actually beat the state of the art by double, the engagement and accuracy and all the metrics. So that's really the power of embeddings and autoencoding, etc. Okay, and before we move on to Netflix, so Jenny asked a question. So, okay, going back to the Google model, did they combine the big model like transformer and the personalized engram model? Yes. So, basically, they kind of give you like two. The details of this are like a little like hard to explain without like going into like NLP like very in depth. But basically, you use an embedding, right, to convert your email into a bunch of word vectors, and then you do a bunch of embeddings, and you basically make the representation of those words very meaningful. So then you have Gmail's large model that represents English language. Give an output of a few words, right, of what it has to predict. But then you also pass it through the ngram model, and the ngram model also gives a few outputs, right? And then what you do is you literally add those outputs together and combine them, and then give that as the result. And that's literally how those two models work together. So it's very simple in how they combine both of the recommendations. Okay, and now let's move on to the last company that we have to discuss about, which is Netflix. So Netflix is actually, out of all the big tech companies, is really known for how it deals with like streaming networks and communications, because you have, for example, even like Facebook, even though it might have more users, when you request data from Facebook, you request a few posts, right? And maybe you refresh your feed like every like minute or so to get new content, but it's kind of like like very like sparse, right? Whereas Netflix, when you're watching a video or TV show, it has to stream like gigabytes of data per user, right? And that's a lot for Netflix to handle, right? So in the olden days when Netflix was slowly scaling up, and it would run into a lot of performance issues, and Netflix would have to really like spend a lot of money to increase the number of servers it had, right? But then Netflix spent a lot of money on its infrastructure and created like very novel ways of like compressing data and like combining the data together so that you can send less data over. And you can kind of see that here. This is like how Netflix's like recommendation works, in addition with how like sends you data. So there's like a lot of details, and obviously we won't be going into most of this because this would require like a whole like class worth of material to cover. But you can just kind of see that there's a lot of complexity in how you handle recommendations. There's offline recommendations where you train a model, and like offline, and then once the model is trained, then you bring it online, and then you have it run. And then there's like nearline, which is like kind of an in between, and then online is like you literally have a recommendation system that's training in real time but also outputting recommendations in real time. So it uses like a combination of three to like give really high quality recommendations. So basically Netflix had to come up with a few metrics, right? Because a lot of like not even you'll see this a lot in business too. Like in business, like a lot of work is driven by metrics and key performance indicators, but so is machine learning, interestingly enough. When you are like iterating on a machine learning model, you have some goal in mind. So the goal might be to increase accuracy by 5%. It might be to decrease the latency by 20%, et cetera, et cetera. So really, it's important to consider good metrics because that really drives the entirety of the like project of whenever you're working on a project that's machine learning related. So two metrics that are used here drove a lot of like Netflix recommendation algorithm development, which is average precision at n and mean average precision at n. So just it seems like very like hard to understand from the like from all the mathematical symbols, but it's actually pretty simple in theory. So if you look at the bottom image, you whenever Netflix has recommendations, it gives you a list, right? And the list is very carefully curated with videos that you're more likely to see earlier than videos that you're more likely to see later, right? Less likely to see later. So if you were to have only three recommendations in the list, then basically it'll tell you like here like correct positive basically looks at so correct positive is when your model predicts that you watch a video and you actually watch the video. A false positive is when the model predicts that you watch a video, but you actually don't watch the video. So here we want to obviously maximize the number of correct positives, right? Because that means our model is more accurate. So then we can see that the average precision at n equals 7, or sorry, n equals 3. Is 1/3, but the average precision at n equals 6 is actually 1/2. So it's like that's like a good like metric to consider, right? Because obviously we want our average precision at n to be higher as we increase. So you can kind of see this trade-off. It's like it's not a very like smooth curve, right? Because we might have like a faulty recommendation, then we might run into a good recommendation, then a bad recommendation, right? So we kind of get a very jagged line for how the model performs. The details of precision recall, we don't have to get into those, but basically just know that it's like not very like mean average precision at n isn't like a very continuous function. It can be very like discrete and jaggedy. And just coming back, basically all you do is you let's say K is you have all these items. So Netflix, the items are videos, right? Or movies and TV shows. Probability of K basically represents what's the probability that you actually like click on the video. And then relevance is like how relevant it is, right? Like how relevant it actually is. And P is the model prediction, right? So we want to like really maximize the average precision at n. And then the mean average precision is we do that over all the users, right? So we find the average precision at n, given that you're a specific user, and then sum that over all the users. So that's basically all these metrics are doing. Even though it looks complex, it's actually pretty simple in theory. And Netflix, very similar, and we saw this in YouTube, right? It's very similar in how its recommendation algorithm works. It has a video corpus that it shortlists out of millions of possible TV shows and movies into potentially tens of thousands of potential recommendations, and then it creates the page, right? Like Netflix is very meaningful, it's very carefully engineered into how the specific videos are placed, right? You don't want to just randomly place them because a video that you might really like to see might be like hidden in like towards the bottom, like really right of the screen, right? So you want to move it towards the top left where you're more likely to see it. And you can see that it's very similar to how YouTube does its ranking and candidate generation. So Netflix, how it does ranking, right? Because I remember YouTube kind of just had one way of ranking. Netflix actually has different ways of ranking for different tasks. And the tasks are as shows, right? You have like a continue watching section where you show like what videos you should continue watching. You might have a trending now screen, and there are like many more, right? There are different rows that you see on Netflix, and each one of them likely has its own like ranking system. So the continue watching ranker, this is the information that it uses, right? So it uses the time elapsed since you last viewed the TV show. So let's say you're watching Money Heist, and then some like maybe a week passed since you viewed it. So that'll be passed into the model. And then the point of abandonment. So like when did you like stop watching it? Where did you stop watching it? Did you like stop watching it in your own home? Because that might have meant that you actually got bored of the TV show, or were you like outside and then you like didn't you just like naturally ran out of time to watch the movie, right? So that's like a very important distinction. And then also the device that you watched it on. If you like stopped watching on your computer, you're more likely to meaningfully kind of deliberately have stopped watching Money Heist. Whereas if it was on your phone, maybe you ran out of battery or something else like that happened. So these features are also called context aware signals. That's just like a lingo for just features. And using all this information, it calculates the probability that a user will continue watching a movie or TV show that they stopped watching before. So basically, what you can kind of deduce from this is that the probability that that you'll rewatch Money Heist is much higher than it is for the show on the extreme right. So that's how the continue watching ranker works. And then you have a trending now ranker, which basically calculates like the temporal trends in the entire user base. Right. So you're much more likely to watch a Christmas movie in November and December than you are in like June. And so those are like seasonal trends, right? Recurring year after year, and like you're likely to see them again and again. And when you have seasonal trends, those are good because then you can like very easily like give meaningful recommendations. But you also want to differentiate from one-off events, right? So, for example, COVID-19. So we're not gonna have, we're not gonna have like another pandemic for a while, and because of that, COVID-19 like leading to an uptick in the watch of like medicine documentaries. Maybe that's not really important to consider when we build recommendations in the future, right? Because it's not an event that's going to happen very often. So we have to differentiate between seasonal trends and then one-off events, and we use that in after differentiating those two, then we use that to like kind of come up with the trending now ranker. And yeah, so yeah, up till now, we basically like covered a lot of big text recommendation systems. Obviously, I left out a lot of details. Like each one of these, I could go over like for multiple lectures. Like there's so much complexity, and that's why it's like working on recommendation systems and being like a recommendation system engineer is so cool because there's so much complexity, and like these are like the main parts of like Google's and YouTube's and Facebook's and Amazon's businesses. So yeah, that is basically the overview of big text recommendation systems. So now we'll be taking a slightly different direction and talking about ethics. So up to like now up till now in the class, we've talked about recommendation systems. What are they? How do they work? How are they used? But we also have to consider what are the negative externalities of using recommendation systems, right? Like not everything is perfect. And we'll talk about why exactly recommendation systems aren't perfect. So the ethics at a glance, right? So reason why we have to consider why recommendation systems sometimes get a bad rep is because recommendation systems are trained on humans, right? Like we're the ones producing the data. We're the ones that are like interacting with Netflix's movies and TV shows, the ones who are buying Amazon's products. So we are inherently biased. Like that's why there are problems with the world, right? Because humans are inherently biased. So as a result, if there's bias in the data, then there's also going to be bias in the actual recommendation system, right? So we see this a lot in general machine learning, where if there's like racial bias or gender-related bias, sometimes these machine learning algorithms might actually reflect that bias and act upon it, right? But we obviously don't want that. We want recommendation systems and we want machine learning algorithms to be as fair as possible. And a large part of ethics is maintaining like a diversity of content on a platform and preventing adversaries from dominating the platform. So in the case of Facebook, we want to make sure that there's like a diversity of political opinions, that it doesn't swing two to the left or two to the right. We want there to be like an even mix between the two, so that like we can have like a good a well-sided debate in for society as a whole. And regarding adversaries, we don't want people who create like fake news articles or like highly inflammatory articles from like being able to cheat the recommendation system and like being able to like dominate the platform. So for example, right, like you have a fake news detector. Fake news detectors, how they work is that they look for certain keywords in a fake news article in articles that are more likely to be like correlated to fake news, right? So if we have the word the is going to be seen in both fake news articles and non-fake news articles. So we're not going to really use that in our like analysis. But if we have a word like extremely important or like extremely urgent, then more often than not, that's going to be that's going to be like a fake news article, right? Like if you have a very well-researched article, well-researched articles tend to not create very like highly like black and white statements. So we can kind of use that information, or adversaries can use that information to like make their content seem more neutral to recommendation system, but still be highly inflammatory. So consideration, thing to consider, one thing to consider about recommendation systems is what's called the prevalence of pro-attitudinal content, which is just a very fancy way of saying that content that is pro-attitudinal, which is in that it's very positive or agreeing, right? So an article that uses words that are generally like positive, that show a agreeing mindset, they're 3 times more likely to be recommended than counter-attitudinal content that's more negative and disagreeing. So if an article is oh, I hate this person, I severely dislike that person, it's there's actually studies conducted where like that gets recommended less to people, to users. And initially that might seem good, right? Like obviously we want like pro-attitudinal content to be like more prevalent than like very inciting, scary, extremely emotional content. But there's also like a downside to this, is that basically adversaries can use that to their advantage, right? So let's say that you're trying to say that COVID isn't real, right? And like in an article, then what happens, if you're an adversary, then initially if you pass that into Facebook, then Facebook's face news detector will be like, okay, like this is a fake news article, let's not spread it. But if you are like smart enough, then what you could do is take your counter attitudinal words and make them pro attitudinal, right? So instead of saying COVID-19 is a complete an utter lie, right? Then you can say that COVID it is generally like a disputed whether COVID-19 is real or not, right? Because that's more of a milder way of saying the exact same thing, right? And from the eyes of a recommendation system, it's not going to know whether you're an adversary or not. So then suddenly, just by changing the words around, by changing counter attitudinal language to the inverse of pro attitudinal language, then it increases the probability that your article gets recommended, right? So that's why you see some fake news detectors don't really work that well, because it's still these adversaries can like kind of circumvent these measures that are put in place. Um, and yeah, you can just see kind of like the graph on the left, like the number of posts that are assigned to a specific user. So pro-attitudinal is about like 65, counter-attitudinal is about 30. And then you can kind of see the percentage from how these for the difference in pro-attitudinal to counter-attitudinal, where these articles came from. And another and again, there are dozens in not if not hundreds of problems with recommendation systems and machine learning algorithms. They're like an entire course worth, but we'll just talk about 2 in this lecture for the sake of time. So another problem that we see are swings in recommendations. So just by viewing a few articles in the opposite political party, what happens with the recommendation systems is they'll largely swing in that direction, especially in Facebook's recommendation systems. That's what this article was trying to look at for Facebook specifically. And you may have observed this on certain platforms, right? Like let's say you're watching like YouTube, right? And for the first 3 videos, you watch like maybe 2 or 3 cat videos, right? And basically how a machine learning algorithm works is that right now it's only seen 3 data points where you like cats. So then it's going to think with 100% probability that you like cats, right? So because of that, like almost every video that you get recommended is going to be a cat video for a while, right? But that's not really what we want. It's just the fact that we didn't have that much data. Whereas if we theoretically watched millions of videos and then we watched 3 cat videos, then there's only like a 3 in 1 million chance that we like cat videos, right? So because of that, sometimes recommendations can really swing in one direction. And from the view of like political parties, that does happen. So what they did here in this article is for a specific user, they kind of like manually shifted the ideology of the user by just like viewing a bunch of like liberal articles or a bunch of conservative articles. And what they found was just by viewing having a 0.1 shift in ideology, you could have a 0.25 shift in the exposure to content in the feed, 0.35 exposure if you're conservative. And it happened for a browsing behavior. There are some cases where it's over 0.1, with conservative even more so. And you can kind of see for sharing behavior as well, right? So basically what this graphic is trying to show is that by making a small change in the short-term shift in like user consuming content, then a recommendation system like really biases itself so that those recommendations kind of continue over time, right? And the effect of this is polarization, right? So we've we've all heard about how in the past like 20, 30 years politics has been very polarized, as maybe it was like hundreds of years ago. And one potential contributor to this is really like recommendation systems. That's why sometimes Facebook gets a bad rep for like promoting very like inflammatory content, is because it picks up a few things that you like, and then it'll just recommend you hundreds and hundreds of like extremely liberal articles or extremely conservative articles, right? And basically because that's what the recommendation algorithm is trying to do. It's trying to maximize the amount of time you spend on the platform. Well, we also have side goals of like maintaining the overall community that's maintained on the platform, the happiness of the users, right? So it's very important to consider those when building recommendation systems. So there are actually 4 articles that talk about this in detail. So if you're really interested in this, because we don't have that much time in lecture, you can kind of look into these, and they're very well written, very easy to understand articles with these graphics that kind of show you how recommendation systems can create bias. And yeah, that basically brings us to the end of the lecture. So now I'll be talking about the final project. So we've basically reached the end of the course content-wise. So, but remember, this is the second to last lecture. We do have a last lecture in 2 weeks, where we'll be covering a little bit more content. But up till now, basically, you should have a fair understanding of how recommendation systems work theoretically, and through the coding assignments of how you somehow tackle these problems. So to kind of put together everything that you've learned, we're creating a final project. So especially we know that some people in the class don't have coding experience. So we didn't want to like create an assignment where you create your own recommendation system, because there are some people who just who like not have as much experience, and it would be very difficult for them. So what we did instead is like an essay, and like an essay or more researchy kind of project, where the task is basically a company. And we found that a big tech company is easier to talk about since they use recommendation systems more prevalently. But you can choose what you like. If you like, maybe want to talk about a startup that uses recommendation systems, then go for it. Then choose a specific recommendation system that the company uses. So Google has like dozens of applications, choose one. And then write a minimum a 1-page paper, but maximum 2 pages that addresses these 6 points. So first, an overview of the company, the services that they use, the overview of the recommendation system that they use, like what's the purpose of it, what's their goal, what are the inputs and the outputs to the recommendation system. And then third, talk about one technical aspect of the system in sufficient detail. So in this presentation for Google, for example, we talked about embeddings, ranking, candidate generation, etc. But if you can talk about one of those things, how they handle that specific aspect, or talk about something that else that's technical, whatever you like. Then talk about the problems that the system may face. So for this, refer back to lecture 1. Remember, we talked about cold start, serendipity, data scaling, things like that. Talk about one problem that that their specific recommendation system tries to tackle. Then fifth, talk about ethical, security, and privacy concerns. So you can kind of talk about like polarization if you're talking about like Facebook's news content, or it can be like something else. It's really up to you. And then lastly, how would you augment the system with one algorithm that we learned in class, and the advantages or disadvantages of this augmentation? So if you're having Facebook's recommendation algorithm, then maybe you can use an RNN to increase the quality of content-based recommendation, right? So it's up to you, but please walk us through your thought process of how you use this algorithm. And then you may include 1 to 2 images to kind of depict the recommendation system, but don't like make the images so big that you write like 1 sentence for each, right? Because we want you through this project to like understand how recommendation system works in detail on your own. And then lastly, we'll please type like a 3-sentence overview of the company and recommendation system that you end up talking about. This is separate from this like 1 to 2 page paper, because as I said in the beginning of lecture, we're going to be presenting these and compiling them for the final lecture. So yeah, that's basically it. We'll release more details in a bit on Piazza. The due date for this is November 30th at 11:59. And that's basically the day before the final lecture, which is on December 1st. So yeah, please have that done by then. And we don't have lecture next week. And yeah, happy Thanksgiving, and we'll see you guys in 2 weeks. If you guys have any questions, I'll be here, and you can ask them on chat, or you can unmute also. Okay. So yeah, Jenny, you asked, is there a quiz and homework for this week? Yes. So as like, I'll go back to like the first, first few slides. Yes. So here you can see like there's a quiz due on Friday, which will release very soon, and then a homework due on Wednesday, and then the final project. Yeah. Yeah, it looks like nobody else has any questions. So yeah, if you guys have any questions, please ask them on Piazza. Oh, can we have updates on lecture 7 and 8? Yeah, right after this, we'll be uploading the recordings on YouTube, and then all of that will be available as well. Yeah.